Welcome. There is nothing you need to do right now, nowhere to be, nothing to solve. Let your breath slow. Let your shoulders sink into whatever is holding you. Tonight we drift far ahead in time, through the quiet future of our universe. Earth's rotation is changing so gradually that leap seconds, once needed almost every year, will be required less and less. The planet's spin is settling into a new, subtle rhythm, and our clocks will barely notice. In 2029, a mountain-sized asteroid named Apophis will glide past Earth, closer than many of our own satellites. It will be visible to the naked eye, a faint moving star crossing the night. No danger will come of it. Astronomers have long confirmed its path is safe. For one evening, people around the world will simply look up and watch a quiet visitor pass by. In 2035, Mars will swing to one of its closest approaches to Earth this century. The red planet will glow larger and brighter in the sky than it has in decades. Telescopes will catch faint hints of its dusty canyons and pale polar ice. For a few weeks, Mars will feel almost near enough to touch. In 2044, a total solar eclipse will once again sweep across the continental United States. The moon's shadow will trace a slow path from coast to coast, dimming towns for a few peaceful minutes. Daylight will fade into a strange twilight, and the sun's corona will glow like a soft silver ring. Then, just as gently, the light will return. In 2061, Halley's Comet will return to the inner solar system, tracing the same long path it has followed for thousands of years. Its icy tail will brighten faintly against the dark, visible from Earth for the first time since 1986. Generations will have passed between one appearance and the next. The comet moves on a rhythm far slower than any single human life. In 2080, Jupiter and Saturn will draw close together again in the evening sky, forming another quiet conjunction. The two giants will appear almost touching from Earth's vantage point, though they remain hundreds of millions of kilometers apart. Their light will blend into a single warm glow at dusk. It happens slowly, a patient alignment written into orbits that never hurry. In 2117, Venus will pass directly across the face of the Sun, as seen from Earth, a rare transit visible only a few times in any century. A small dark dot will inch slowly over the bright solar disk. Observers with proper filters will watch it cross in complete silence. It is one of the sky's most unhurried performances. In 2125, Saturn's rings will once again turn edge, on toward Earth, thinning until they nearly vanish from view. For a brief span, the planet will appear almost bare, a pale sphere without its familiar halo. Then the rings will slowly tilt back into sight, as they have every 15 years or so. Saturn keeps this gentle rhythm across centuries. In 2178, Pluto will complete its very first full orbit around the Sun since its discovery in 1930. Nearly 250 years will have passed for a single lap around our star. Everyone who first saw Pluto through a telescope will be long gone by the time it returns to where it began. The little world moves at its own unhurried pace. Atomic clocks are precise enough that within a few decades, they will detect measurable relativistic time drift across Earth itself. Clocks placed at different elevations already tick at faintly different speeds, a whisper of Einstein's relativity built into gravity. Mountain labs run microseconds ahead of valley labs. It is a small, steady reminder that time is not the same everywhere, even here at home. Let your breath find its own rhythm now, without any effort to guide it. Notice the pause after each exhale, that small hush before the next breath arrives. Let that pause grow, just slightly, each time it comes. Your shoulders can settle into the mattress, heavier with every outbreath. There is only the slow tide of air moving in and moving out, carrying you further from thought and closer to rest. Sea levels will keep rising for centuries to come, driven by ice sheets already retreating. Greenland and Antarctica hold enough frozen water to eventually lift oceans by many meters. This melt unfolds across generations, not headlines. Coastlines familiar today will be redrawn, inch by inch, long after anyone alive now remains to watch the new shoreline settle into place. Voyager 1's radio signal will grow too faint to detect within about a century. The spacecraft's nuclear battery loses power year after year, its transmission thinning like a candle glimpsed far down a long hallway. Even now, its signal takes almost a full day to reach Earth, crossing a distance beyond ordinary imagining. Eventually, Voyager will drift on in complete silence, unheard but never truly gone. Polaris will lose its place as the North Star within a few centuries, as Earth's axis continues its long, wide circle through the sky. The pole is already drifting away from Polaris, a sliver of arc each year. Future navigators will look toward an empty patch of sky where Polaris once sat, and eventually toward another star entirely. The night sky keeps rearranging itself, always, even if we notice only rarely. Most languages spoken today will evolve beyond recognition within 1,000 years. Sounds shift, grammars bend, and words drift into new meanings so gradually that no single generation notices the change. Old English already reads like a foreign tongue to modern eyes, separated by only about 1,000 years. Whatever language a future descendant speaks, it will carry echoes of ours, distant and reshaped, like a river that has changed its banks but still remembers its source. The Great Pyramid of Giza will show only minor erosion after 1,000 years, its limestone core largely unmoved by wind and time. Built more than 4,000 years ago, it has already worn away the outer casing stones that once made it gleam white in desert sun. What remains beneath has settled into something closer to permanence. Stone, it turns out, keeps its own kind of patience. Earth's magnetic North Pole will wander far from its current position within 5,000 years, tracing an unpredictable path across the Arctic. It has already drifted hundreds of kilometers over the past century alone, pulled by molten currents deep inside the planet. Compasses will point somewhere new, though the shift unfolds too gradually for any single lifetime to notice. The planet's inner engine keeps turning, indifferent to the maps we draw above it. The Ice Age cycle will likely push Earth toward a new glacial period within 10,000 years, following a rhythm written into the planet's orbit. Small wobbles and tilts in Earth's path around the Sun have triggered ice ages roughly every 100,000 years throughout its recent history. Vast sheets of ice will creep across continents again, reshaping coastlines and burying forests beneath white silence. It has happened many times before, and geology suggests it will happen again. Vega will become the pole star in about 13,000 years, taking its turn in a slow rotation of stars that has cycled through this role for ages. Ancient civilizations once aligned monuments to different stars entirely, following the same wandering pole. Vega already shines as one of the brightest stars in northern skies, blue-white and brilliant. One day it will sit almost precisely above Earth's axis, watching over a very different world. Earth completes one full wobble of its axis roughly every 26,000 years. A motion astronomers call precession. This slow circling traces a wide loop through the sky, carrying the position of the pole from star to star across ages. Polaris, then Vega, then stars not yet named as guides. Each will take a turn marking north. It is one of the planet's oldest, longest rhythms, older than any calendar humans have kept. 40,000 years from now, Voyager 1 will drift within a few light years of a star called Ross 248, still coasting through interstellar space. It carries no fuel and no destination now, only the momentum given to it decades ago. Its radio voice will have gone dark long before this encounter, though its metal frame may endure far longer. The craft will pass that star closer than our sun's nearest stellar neighbor, an unannounced visitor drifting through the dark. Feel the weight of your body now, settling deeper into the mattress beneath you. Let your feet grow heavy first, then your legs, sinking like stones into warm sand. That heaviness climbs upward, through hips, chest, and shoulders, each part letting go of the day it carried. Your arms rest wherever they land, no longer needing to hold anything up. Even your head presses a little further into the pillow, heavy and still, as though gravity itself were drawing you toward rest. Niagara Falls will finish wearing itself away in about 50,000 years, the same erosion that has already carried it 11 kilometers upstream since the last ice age. Each year the rushing water carves back the rock face by a small measure, retreating toward Lake Erie a little further. Eventually the falls will reach the lake itself, and the thunderous drop that draws millions of visitors today will flatten into an ordinary stretch of river. The water will keep moving, only lower and closer to its source now. Familiar constellations will lose their shapes within about 100,000 years, as each star follows its own path through the galaxy. The Big Dipper's stars are already drifting apart at different speeds, some rushing away while others linger. Orion's belt, Scorpius's curve, every outline we've named will stretch, bend, and eventually dissolve into new patterns. The stars themselves will remain, bright as ever, but the pictures humans drew between them will belong only to this moment in time. Betelgeuse, a red giant many times larger than our Sun, may end its life in a visible supernova sometime within the next 100,000 years. When it happens, the explosion will briefly outshine every other star in the night sky, visible even in daylight for weeks. The star sits about 600 light-years away, close enough to dazzle yet far enough to pose no danger to Earth. No one yet knows the exact night it will happen, only that the star is already living its final chapter. Comet Hale, BOP is due to swing back through the inner solar system around the year 4385, completing an orbit that stretches across more than 2,000 years. It dazzled skywatchers in the late 1990s, one of the brightest comets seen in generations, with two tails glowing across the night. By the time it returns, human history as we know it today will lie deep in an unimaginable past. The comet keeps its own calendar, indifferent to the centuries passing beneath it. Neptune will complete its very first full orbit since its discovery in the year 2846, having taken almost 165 years to circle the Sun once. Astronomers first spotted the planet in 1846, guided by mathematical predictions before anyone ever saw it directly through a telescope. Its blue, wind-swept surface will have circled the Sun only once across 2 centuries of human history. Time moves differently out there, marked not in years, but in a single unhurried lap around a distant star. Earth faces a statistical likelihood of being struck by a city-scale asteroid sometime within the next 500,000 years, based on the frequency of past impacts recorded in craters worldwide. Such an object, perhaps a kilometer wide, would strike with enough force to devastate a region, though not the entire planet. Space agencies already track thousands of near-Earth objects, refining their orbits year after year. Impacts of this size have happened before across Earth's long history, and the odds simply describe rhythm, not any specific date. Grand Canyon will carve itself substantially deeper within the next million years as the Colorado River continues cutting through layers of ancient rock below. The canyon already reveals nearly 2 billion years of Earth's history in its striped walls, layer stacked upon layer like pages in a book. Each flood and each trickle removes a little more stone, deepening the gorge by fractions of a millimeter at a time. Someday the walls will stand taller still, telling an even longer story to whoever stands at the rim. Continents will shift by several kilometers within the next 2 million years, drifting atop slow-moving plates of rock beneath the crust. Africa's edges will inch further from South America, while Australia continues its steady drift northward toward Asia. These plates move roughly as fast as a fingernail grows, imperceptible within any human lifetime, yet unstoppable across deep time. Mountains rise, oceans widen, and the map of the world keeps rewriting itself, one fingernail's width each year. Orion's brightest stars will drift far enough to break its familiar shape within 8 million years. Betelgeuse, Rigel, and their neighbors move independently through the galaxy, each following its own path around its distant center. These separate motions will pull the hunter's outline apart, star by star, over that span. The 3 stars forming Orion's belt will spread until they no longer align. Whoever watches the sky then will trace a shape nothing like the one above us tonight. Beneath East Africa, tectonic forces are already pulling the land apart, promising a new ocean within 10 million years. The Great Rift Valley stretches from the Red Sea south through Ethiopia and Kenya, where the crust thins a little more each year. Molten rock rises underground, pushing the land in 2 directions at once. Somalia and the rest of the continent will separate, letting seawater flood the widening gap. A new coastline will someday mark where solid ground once stood unbroken. Somewhere beyond these walls, a low hum settles into the air, rising and holds, then fading like a breath moving through an old house. Listen without trying to name it. It arrives, stays a moment, and lets go again. Your shoulders can loosen a little more each time it recedes, sinking heavier into the mattress. There is no need to follow it anywhere. Let it come, let it pass, and rest in the space it leaves behind. Mars's small moon, Phobos, spirals a little closer to its planet each year, and within 40 million years it will likely crash into Mars or break apart into a ring. Unlike Earth's moon, which drifts outward, Phobos orbits so near that Martian gravity tugs it steadily inward. Tracking its path, researchers expect the moon to eventually cross a threshold where tidal forces overwhelm its structure. It may shatter into a thin ring circling Mars or plunge directly into the dust below. Either ending would rearrange the Martian sky. Africa will press northward across the coming 50 million years, closing the Mediterranean Sea against the shores of Europe. The African plate continues its steady march, narrowing the sea a little more with each passing age. Mountain ranges will rise where seafloor once lay, folding upward as the 2 landmasses finally meet. The Mediterranean's blue basin, home to countless coastal cities today, will vanish beneath new highlands entirely. Where sailors once crossed by boat, distant descendants might someday walk mountain passes. California's coastline will slide roughly 50 million years further north along the San Andreas Fault, carried by the same forces reshaping the whole Pacific Rim. The fault marks where 2 great plates grind past each other, inching Los Angeles closer to San Francisco with every passing century. This movement, just a few centimeters a year, will eventually carry the western sliver of California past its northern neighbor. Baja California may separate from the mainland entirely, forming a long island where the fault runs beneath the sea. Saturn's rings will vanish completely within 100 million years, dissolving as icy particles rain steadily into the planet's atmosphere. Saturn's gravity constantly pulls ring material downward, a slow fall of ice and dust into the clouds below. Spacecraft observations already show this erosion happening today, faster than researchers once assumed. Without new material to replace what falls, the rings will thin year after year until nothing bright remains. Saturn will still turn in sunlight, but its signature halo will have disappeared entirely. Each passing age stretches Earth's day a little longer as the moon's retreat drains momentum from our planet's spin, Tidal friction between Earth and Moon transfers rotational energy outward, pushing the Moon into a wider orbit while Earth's spin eases. Ancient days lasted several hours shorter than today's, and future days will stretch several hours longer still. Millions of years from now, a single sunrise to sunset cycle might span far beyond what any clock face was built to show. The change happens too gradually to notice in a lifetime, yet it never stops. A new supercontinent will assemble from today's scattered landmasses within 250 million years, closing today's oceans into a single vast basin. Geologists have named this hypothetical landmass Pangaea Proxima, following patterns traced from plate movements already underway. Continents drift together and apart in a rhythm as old as the planet's crust itself, a cycle already repeated across Earth's long history. The Americas, Africa, Europe, and Asia may merge into one enormous landmass surrounded by a single global ocean. Mountains taller than any today could rise where continents finally meet. The Moon's steady retreat will weaken its pull on Earth's oceans, easing tides that once rose and fell with far greater force. Billions of years ago, a closer moon dragged tides many meters higher than today's, reshaping coastlines with tremendous daily force. As the moon keeps drifting outward, its gravitational grip on ocean water grows weaker with each passing era. Future tides will rise and fall more gently, guided by a moon growing ever more distant in the sky. Beaches that flood dramatically today may someday see only modest swells. Within 600 million years, the moon will have drifted far enough that it can no longer fully block the sun. Total solar eclipses, once perfect and complete, will become annular instead, leaving a thin ring of sunlight glowing around the moon's edge. This shift happens as tidal forces push the moon a little farther from Earth each year. Future observers, whoever they might be, will look up and see something softer, a corona interrupted rather than eclipsed. Rising solar brightness will begin disrupting Earth's carbon cycle within that same distant span of time. As the sun burns brighter, weathering of rock intensifies, drawing carbon dioxide out of the atmosphere faster than volcanoes can replace it. Plants that rely on photosynthesis may struggle as levels grow too thin to sustain them. Earth's climate, so finely balanced for billions of years, would begin tipping toward a warmer, less hospitable state. Earth's oceans will boil away entirely within about 1 billion years, as solar output keeps climbing beyond anything life today could endure. Water vapor rising into the upper atmosphere will break apart under sunlight, its hydrogen escaping into space forever. Rivers and seas will shrink first to puddles, then to memory. What was once a blue and abundant world would turn parched, its surface baked under an unrelenting sky. Let warmth begin somewhere small, perhaps behind your eyes or low in your chest, and let it spread from there. Feel it move into your shoulders, loosening what the day left tight. Let it flow down through your arms, into your hands, until even your fingertips feel heavy and warm. Let it pool in your stomach, then travel down through your hips, your knees, your feet, until your whole body rests in the same steady warmth, held and unmoving. Andromeda will loom far larger in Earth's sky within about 1 billion years, no longer a dim patch of light, but a sprawling glow stretching across the night. Its light will spill from horizon to horizon, dimmer than the moon, but far wider, a pale river of stars overhead. Anyone standing beneath it would see two galaxies now approaching each other, still separated by vast distance, but closing in. The sky itself would look different from any human has ever known. Earth's core may cool enough within 2 billion years to weaken the magnetic field that has shielded the planet since its earliest days. As the molten outer core loses heat, the dynamo driving our magnetism could slow and falter. Without that shield, solar wind would strip away more of the atmosphere over time, exposing the surface to radiation once held at bay. Geophysicists are still refining how fast this cooling might proceed. In about 2.5 billion years, Andromeda will begin its slow collision with the Milky Way. The two galaxies will pass through each other gradually, their stars mostly slipping by without touching, since space between stars is so vast. Gas clouds will compress and ignite, sparking bursts of new star formation across both galaxies. From within, the night sky would fill with more light than it has held in ages. Milkomeda is the name astronomers have given to the single galaxy that will form once the Milky Way and Andromeda fully merge. Over several billion years, their spiral shapes will dissolve into one another, settling into a smoother, rounder form. Stars, once belonging to two separate galaxies, will orbit a shared center, their old boundaries lost to time. What began as two bright disks will end as one great elliptical blow. Mars could briefly become more Earth-like as the Sun continues to brighten over the coming billions of years. Warmth that once could not reach the red planet's frozen surface may finally thaw buried ice, releasing water and thickening a once thin atmosphere. For a window of time, rivers could flow again across ancient channels long dry. It would be a fleeting habitability, arriving only as the inner solar system grows too hot for the world it once favored. 4 billion years from now, most of Earth's surface water will have vanished, lost gradually to a sun too bright for oceans to survive. What remains will cling to deep basins or hide beneath ground, shrinking pockets in a world otherwise scorched dry. The blue marble, long familiar in photographs, would fade into browns and grays. It marks one of the last thresholds before Earth's surface becomes truly inhospitable to anything alive. 5 billion years from now, the Sun will have burned through the hydrogen fuel that has powered it since Earth was young. Its core will contract under its own weight, growing denser and hotter with nothing left to hold back gravity's pull. Fusion will shift outward into surrounding layers, changing the balance that once kept the Sun steady. The star that has warmed every sunrise in human history will begin, quite literally, to run out of breath. Roughly 5.4 billion years from now, the Sun will swell into a red giant, its outer layers ballooning far beyond their current reach. It will grow hundreds of times larger than it is today, glowing a deep orange-red across the sky. The transformation will unfold gradually, over millions of years, as the star's structure rearranges itself from within. What once fit neatly within Mercury's orbit will stretch far past it. Mercury and Venus may not survive the Sun's red giant phase at all. As the outer layers of the star expand outward, they could reach far enough to swallow both inner worlds whole. Mercury, closest and smallest, would offer little resistance to the engulfing plasma. Venus, though larger, would likely fare no better, its rocky surface consumed by the star it once orbited closely. Earth may drift into a wider orbit as the Sun loses mass during this expansion, its gravitational grip loosening just enough to let our planet slip further out. That small shift could be the difference between survival and engulfment. Even so, the widened orbit would offer little comfort, since a scorched and lifeless Earth would still circle a swollen, dying star. Escape, in this case, would mean surviving as ash, rather than as a living world. Somewhere in a still room, dust hangs, suspended in a single beam of light, moving so slowly it seems almost motionless. Each fleck drifts without hurry, unbothered by time, content simply to exist in the air. There is no need to follow its path or understand its pattern. Let your breathing settle into that same unhurried rhythm, weightless and slow, needing nowhere else to be tonight. Outer layers of the Sun will spread outward into space, forming what astronomers call a planetary nebula. Delicate shells of glowing gas will expand around the star's exposed core, lit from within by the heat still radiating outward. For a brief span, by cosmic standards, this structure will shimmer visibly across nearby space. Then, like a lantern slowly losing its flame, the glow will fade as the gas disperses. By 8 billion years from now, the Sun will have settled into its final form as a white dwarf. Dense, small, and no longer fusing atoms at its core, it will glow faintly from stored heat alone. There will be no more expansion, no more transformation, only a long, slow cooling that stretches across unimaginable spans of time. What remains will be little larger than Earth, yet unimaginably heavier. Most Sun-like stars scattered across the universe will have died out by 10 billion years from now, their fuel exhausted in much the same slow decline. Each one, in its own corner of its own galaxy, will pass through a similar arc: growth, brightness, expansion, and quiet collapse into a dim ember. The pattern repeats endlessly, star after star, across countless galaxies. It is less an ending than a shared rhythm written into the nature of stars themselves. The local group of galaxies will finish its long merger, settling into one giant elliptical galaxy where separate spirals once turned independently. Milkometa, along with smaller nearby galaxies drawn in over eons, will blend into a single smooth structure. Old boundaries between galaxies will lose all meaning, replaced by one shared gravitational center. What was once a scattered neighborhood of galaxies will become a single, quiet home. Galaxies beyond the local group will vanish from reach, carried away by the ever-quickening expansion of space itself. Their light, already faint across such distances, will stretch and fade until it can no longer be detected at all. From within the merged local group, the night sky will empty of distant neighbors, leaving only the glow of one's own galactic home. The universe will not have shrunk, but it will certainly feel more alone. The last visible quasars will fade as their fuel supplies run out. These brilliant cores, once fed by matter spiraling into black holes, will run dry of the gas and dust that once lit them from within. Without fresh material to consume, their brightness will dim across incomprehensible stretches of time. What once outshone entire galaxies will quietly go dark, leaving no beacon behind. Globular clusters orbiting Milkometa will gradually spiral into its core. Pulled by gravity over immense timescales, these tight balls of ancient stars will lose their outer orbits one by one. Slowly, they will drift closer, their paths tightening like loosening threads pulled inward. Eventually, they will merge into the dense heart of the great merged galaxy, adding their light to its center. Star formation across the merged local group galaxy will mostly cease. The clouds of hydrogen gas that once collapsed into new stars will have been used up or scattered, too thin to ignite. Without fresh material, the great galaxy will stop producing new light of its own. Only the stars already born will remain, growing older together in the same shared structure. New star formation across the entire universe will effectively come to an end. Not just in one galaxy, but everywhere, the raw material for making stars will finally run too scarce to sustain the process. Galaxy after galaxy, the same quiet exhaustion will unfold. The universe will hold its full population of stars already, with nothing left to add. The cosmic web of galaxy filaments will have fully dispersed due to accelerating expansion. Those vast threads of galaxies, once strung together by gravity across billions of light years, will stretch and separate until no connection remains visible. Each remaining galaxy cluster will drift alone, cut off from what once bound it to its neighbors. The universe will no longer resemble a web, but scattered islands adrift in an ever-widening sea. Let your jaw loosen now, the way a held breath finally lets go. Feel the small muscles around your eyes give up their grip, lid by lid, until nothing there is holding on. Behind your closed eyes, there is only a soft, dark field, wide and undemanding. Let your face become unreadable, smooth as still water, asking nothing of you at all. Rest there, in that private dark, for as long as you like. Red dwarf stars will still be quietly burning after 1 trillion years. These small, dim stars use their hydrogen so sparingly that their lifespans stretch far beyond anything else in the universe. Long after brighter stars have died, red dwarfs will remain, glowing faintly with a patience built into their very nature. They will be, for a very long while, the last stars still making their own light. The smallest red dwarfs will finally exhaust their hydrogen fuel. Even the most frugal stars cannot burn forever, and eventually their reserves will run down to nothing. As the last fuel is spent, their faint glow will dim further still, fading toward a quiet end. What took 1 trillion years to unfold will close in a long, gradual fade, rather than any sudden collapse. Most stars in the universe will have burned out into white dwarfs. Across countless galaxies, the ordinary stars that once filled the sky with light will have completed their arcs, collapsing into dense, cooling embers. What remains will be small, heavy, and faint, holding the memory of a star's life in compressed form. The universe, once brilliant with starlight, will grow steadily dimmer as this transformation spreads. White dwarfs will begin slowly cooling toward becoming inert black dwarfs. With no fusion left to sustain their glow, they will radiate away their remaining heat into the cold of space. Over spans of time longer than the universe has yet existed, their light will fade toward nothing. Eventually, they will sit dark and silent, cold remnants marking where stars once lived. Brown dwarfs will contract and cool without ever igniting fusion. Too small to sustain the pressures needed for true starlight, they spend eternity as failed stars, dim from the very beginning. Over vast stretches of time, they shrink further, tightening under their own gravity. Their glow, always faint by stellar standards, will fade toward the same dark stillness, awaiting the stars around them. They ask nothing of the universe and receive nothing back. The universe's total luminous energy output will drop to a tiny fraction of its peak. Where galaxies once blazed with billions of newborn stars, only embers and dying giants remain to shine. Each passing age dims the cosmos further, the great furnaces of creation falling still one by one. What once filled space with brilliance now offers only scattered points of feeble light across immeasurable darkness. Planetary orbits will begin destabilizing from rare gravitational encounters. As stars drift and pass one another across unthinkable spans of time, their gravity occasionally tugs at nearby planetary systems. Most encounters are gentle, distant, barely noticeable. But over eons, enough of these subtle nudges accumulate to loosen orbits once thought permanent. Worlds that circled their stars in perfect rhythm for billions of years will slowly wander from their paths. Free-floating planets will wander interstellar space after ejection from dead systems. Cut loose from any star, these rogue worlds drift silently through the vast emptiness between galaxies remaining light. No sunrise warms their surfaces, no star anchors their motion. They travel alone, carried only by momentum, crossing distances that dwarf anything measured in a human lifetime. Somewhere out there, countless such worlds continue their solitary journeys. Most remaining planets will be ejected entirely from their dead star systems. Gravitational encounters, accumulating across trillions of years, eventually break the bonds holding worlds to their stellar remnants. One by one, planets slip free of their orbits and drift outward into open space. What once were organized systems, neat and cyclical, dissolve into scattered debris, moving through the wider dark. Very little stays where it began. Binary star systems will gradually spiral inward, or fly apart via gravitational radiation. Paired stars, bound together since their birth, lose tiny amounts of orbital energy as gravitational waves ripple outward from their motion. Across immense timescales, this steady loss draws some pairs closer until they merge, while others, disturbed by outside forces, drift apart entirely. Either way, the long dance these stars once shared eventually comes to its own quiet resolution. Notice your breath moving without any effort from you. It arrives, it lingers, it leaves, and another follows in its place. There is no need to shape it or hurry it along. Let the exhale grow a little longer each time, a little heavier, sinking further into the stillness beneath it. With each breath released, your body settles a fraction deeper into rest, needing nothing more than this simple rhythm to carry you toward sleep. Galaxies will lose most of their stars to ejection into intergalactic space. Gravitational interactions within crowded galactic cores fling stars outward one by one, sending them beyond the galaxy's edge entirely. Over enough time, this steady leakage strips away the majority of a galaxy's population. What remains grows sparse and thin, a shadow of the crowded structure it once was, its stars scattered far across the surrounding dark. Black dwarfs will vastly outnumber any remaining active stars. As white dwarfs finish cooling into their final dark state across timescales longer than the universe has yet existed, they will accumulate steadily while true stars grow ever rarer. Eventually, for every star still producing light, uncountable dark stellar corpses will drift nearby, cold and finished. The universe's population, once dominated by brilliance, will belong instead to silence and stone, like remnants. Galactic halos will retain only their dimmest, longest-lived stars. The bright, massive stars that once lit a galaxy's outer reaches will have long since burned through their fuel and died away. What lingers in these thin, extended regions are the frugal, low-mass stars built to last far beyond their brighter companions. Spread thinly across enormous volumes, they offer the faintest suggestion of light in what has become an otherwise empty expanse. Stellar remnants will settle into either galactic cores or deep interstellar space. As galaxies age far beyond their star-forming years, gravity sorts their leftover material into two distinct fates. Some remnants spiral inward, joining the dense population near a galaxy's center. Others are cast outward, drifting into the emptiness between galaxies entirely. This long sorting reshapes what remains of a galaxy's structure, leaving a crowded core and a thinly scattered outer reach. Two brown dwarfs, drifting through the emptiness between stars, will occasionally collide. Such meetings are rare, given the vast distances separating these dim, failed stars. When they do merge, the sudden compression can briefly reignite nuclear fusion within their combined core. For a short while, a new point of light flickers where two dark bodies once wandered separately. Then, fuel spent, the newly formed star fades back into darkness. Rogue stellar remnants will drift for eons through the empty space between galaxies. Cast loose by gravitational encounters or the unraveling of their home systems, these wandering white dwarfs, neutron stars, and black holes carry no light of their own to reveal them. They cross distances that dwarf entire galaxies, unanchored to any structure. Across such stretches of time, their journeys become the only motion in an otherwise still expanse. The merged Milkomeda galaxy will have lost the majority of its stars. Through countless gravitational encounters within its crowded core, star after star gets flung beyond the galaxy's reach. What was once a brilliant, densely packed spiral becomes a sparse remnant of its earlier self. The stars that remain cluster mostly near the center or drift thinly through its outer halo, a fraction of the population it once held. Stellar, mass black holes will sink toward galactic centers, pulled inward across eons by a process called dynamical friction. As these dense remnants move through a galaxy's stellar population, their gravity drags against surrounding matter, bleeding away orbital energy. Bit by bit, their paths tighten and descend toward the core. Across enough time, nearly every stellar mass black hole in a galaxy finds its way inward, joining the dense company gathered there. Orbital decay will pull remaining stellar remnants into central black holes. As white dwarfs, neutron stars, and smaller black holes lose orbital energy through gravitational radiation and encounters with other bodies, their orbits shrink year by year. Eventually, each remnant crosses the point of no return, drawn permanently into the black hole waiting at the galaxy's heart. This steady consumption reshapes the galaxy's core into an ever more massive, ever more solitary object. Most matter in Milkomeda will have fallen into or been flung from its black hole. Between the steady pull of gravitational sinking and the sudden ejections triggered by close stellar encounters, almost nothing remains untouched. What began as a galaxy of hundreds of billions of stars empties out through these two opposite fates. The central black hole grows heavier with each captured remnant, while the space around it grows ever more sparse. Let your body grow heavy now, starting at your feet. Feel them rest fully into the mattress, releasing any last hold they had on movement. Let that heaviness climb into your ankles, your calves, spreading upward like something heavy settling deeper with each passing moment. Your hips sink, your shoulders sink. Even your hands, resting wherever they lie, feel too heavy to lift. There is nowhere this weight needs to go, and nothing left for you to carry tonight. As organized structures, galaxies will have essentially dissolved. The spirals, bars, and halos that once gave them shape depend on countless stars moving together under shared gravity. As stars are ejected, absorbed, or extinguished, that shared structure unravels into isolated remnants and thin scatterings of dark matter. What once resembled a great cosmic city becomes an indistinct field of drifting relics, with no clear center and no recognizable form remaining. Rare collisions between degenerate stellar remnants will occasionally forge new points of light. When two white dwarfs or neutron stars happen to meet across the emptiness, the resulting merger can trigger a brief burst of fusion or a violent release of energy. For a moment, a spark of brightness interrupts the surrounding dark, visible across immense distances to anything still watching. Then the light fades, and the remnant settles back into stillness, indistinguishable once more from its silent surroundings. Neutron stars will occasionally collide, producing brief bursts of heavy element creation. When two of these dense remnants finally spiral together, the impact forges elements far heavier than iron, including gold, platinum, and uranium. Astrophysicists call this event a kilonova. For a short while, the collision outshines entire galaxies before fading into the surrounding dark, scattering its newly made elements outward into whatever space remains. Deep within degenerate matter, fusion may eventually push all the way to iron, forming what physicists call iron stars. Because iron holds the most stable atomic nucleus, quantum tunneling could, across almost unimaginable stretches of time, convert lighter elements inside dead stars into it. This process would unfold far slower than anything observed today. If it happens at all, it belongs to timescales longer than the universe has yet existed. Proton decay, if real, would begin dismantling atomic nuclei one particle at a time. Grand unified theories suggest protons might not last forever, though experiments have never caught one in the act. Should this decay occur, it would work with extraordinary patience, unraveling matter itself across timescales vastly longer than stars have burned. Physics still holds this as an open question, rather than a settled fact. Under certain theories of quark matter, neutron stars may eventually convert entirely into a stranger form called strange quark matter. If quarks inside their cores break free from ordinary confinement, the whole star could transform into what researchers term a strange star. From the outside, little would visibly change. The transformation would occur deep within, invisible to any distant observer. Rather than radiating light, like their earlier stages, black dwarfs will lose mass mainly through proton decay. Having cooled past the point of meaningful photon emission, these ancient stellar remnants sit in near total darkness. Whatever proton decay slowly does to matter becomes their only remaining transformation. It happens without light, without heat, and without anything left to witness it. Most ordinary matter in the universe will have decayed into pure radiation. The protons and neutrons that once built stars, planets, and every familiar object will have unraveled into photons and lighter particles. What began as a universe rich with solid structure ends this stretch of time as something closer to a faint field of energy. Matter, in its recognizable form, becomes exceedingly rare. Eventually, black dwarf stars will fully decay away, leaving only black holes behind. Once proton decay finishes its long work, these last stellar remnants lose their remaining structure entirely. What once resembled cold, dead stars simply ceases to exist as matter. Across the wider universe, black holes become the only structures still holding any defined shape. The smallest black holes formed from planets will evaporate first through Hawking radiation. Because evaporation time depends heavily on mass, these lighter black holes complete the process long before their heavier stellar cousins. Their disappearance releases one final burst of radiation into the surrounding emptiness. It marks the quiet end of the smallest structures gravity ever managed to hold together. A hum arrives from somewhere far off, low and steady, like wind moving through a house that has settled for the night. It rises just enough to notice, then eases back into stillness. Let it come and go without following it anywhere. Your breath can match its rhythm, rising, falling, asking for nothing else. Each time the sound fades, let your body sink a little further into the bed beneath you. Even black holes born from ordinary stars will fully evaporate through Hawking radiation. Their disappearance takes far longer than the planet-sized ones before them, stretching across timescales almost beyond description. Yet mass alone cannot save them from this slow unraveling. When the process finally completes, another small piece of the universe's remaining structure quietly disappears. Black holes, carrying the original stellar mass of galaxies like the Milky Way, will finally complete their evaporation. Each one formed from a collapsed star, patient through unimaginable stretches of time, releasing Hawking radiation so faint it barely registers as anything at all. Across incomprehensible ages, that trickle adds up. What once anchored a galaxy's structure disperses into a whisper of particles, and another category of cosmic memory closes. Supermassive black holes, holding billions of times the mass of our Sun, will be the very last to dissolve. Sitting once at the hearts of galaxies, they outlast every star, every remnant, every smaller hole around them. Their evaporation stretches across timescales so vast that ordinary numbers lose meaning. When it finally happens, it closes an era where gravity organized the universe into anything recognizable. Primordial black holes, if such objects truly exist, would be among the very first to vanish entirely, formed not from dying stars, but from the density fluctuations of the newborn universe. Some were small enough to have evaporated ages before this point. Physics has no confirmed evidence they exist, only theoretical grounds for suspecting they might. Their disappearance, wherever it occurred, would have gone unnoticed by anything alive to witness it. Virtually every black hole across the universe will, by this point, have evaporated away. From the smallest planetary remnants to the grandest galactic anchors, none endure forever under Hawking's slow radiance. Gravity's most extreme structures, once thought permanent, dissolve given sufficient time. Nothing built from collapsed matter remains standing. What's left behind is a universe without its darkest, densest landmarks. By now, the universe holds little more than a thin gas of photons and leptons, spread across distances too enormous to picture. Protons, neutrons, and the atoms they once built have long since broken down or drifted beyond reach of one another. Light particles and their lightweight cousins occupy what was once filled with galaxies. Space becomes less a stage for objects and more an endless, dilute mist. Neutrinos will vastly outnumber every other kind of particle still moving through space. These nearly massless, barely interacting particles pass through whatever remains without resistance or collision. They carry no charge, build nothing, and rarely meet another particle across unfathomable distances. In sheer numbers, though, they dominate what little population the universe still contains. Spontaneous quantum fluctuations may become the only source of anything resembling new structure. Physics allows for these brief, random appearances of energy from otherwise empty space, though they vanish almost as quickly as they arise. Cosmology has no confirmed account of what, if anything, endures from them. In a universe this empty, even the smallest flicker counts as an event worth marking. Rare quantum tunneling events could spontaneously produce particles seemingly from nothing, straight out of the vacuum itself. This isn't mere speculation. It follows directly from the uncertainty built into quantum theory. In a universe this sparse, such fleeting particle pairs might be the closest thing left to activity. They appear, exist briefly, and disappear again, leaving the vacuum exactly as still as before. Positronium atoms, strange pairings of an electron and its antimatter twin, may form and decay as some of the very last atoms the universe ever produces. They don't last. The two particles eventually annihilate each other in a burst of energy, converting mass fully into light. Even this fleeting structure represents something rare in an era defined mostly by emptiness. Their brief existence and quick dissolution echo the pattern the whole universe now follows. Let warmth begin somewhere small, maybe the center of your chest, and let it spread from there without any hurry behind it. It moves into your shoulders next, loosening what you didn't notice you were holding, down through your arms, into your fingers, until your hands feel heavy and full, down through your stomach, your hips, your legs, all the way to your feet, until the warmth has reached every part of you and settled there, staying as long as you need it to. Entropy across the universe will keep climbing toward its highest possible level, a state cosmologists call heat death. Energy would spread so evenly that nothing could concentrate into stars, motion, or thought. No temperature differences would remain to drive any kind of process. Everything reaches the same, faint, uniform hum of stillness. It is less an ending than a leveling, the last difference finally smoothed away. One theoretical fate, called the Big Rip, would tear apart every bound structure if dark energy continues to strengthen over time. Galaxies would separate first, then stars, then planets, and eventually atoms themselves. The expansion would accelerate so quickly that nothing could hold together against it. Physics allows this outcome under certain models, though it remains unconfirmed. It stands as one possible ending, among several the far future might choose. Another theoretical fate, the Big Crunch, would reverse cosmic expansion entirely if dark energy someday weakens rather than grows. Distances between galaxies would slowly begin shrinking instead of widening. Temperatures would rise as everything drew back together toward a single dense point. Current measurements make this scenario appear unlikely, though it cannot be fully ruled out. It offers a mirror image of the beginning, expansion undone in reverse. A third scenario, the Big Freeze, describes a universe expanding forever into darkness that only grows colder with time. Under this model, nothing tears apart and nothing collapses back. Space simply keeps widening, diluting whatever light and heat remain. Most current evidence points toward some version of this quiet, cold continuation. It is the gentlest of the three futures, an ending built from patience rather than violence. Vacuum decay describes a theoretical shift in which the universe's underlying energy state could drop instantly to a lower, more stable level. If it happened, the change would ripple outward at nearly the speed of light, rewriting the rules of physics as it passed. No warning would precede it, and no observer could outrun it. Whether our universe's vacuum is truly stable remains an open question in theoretical physics. For now, it stays a quiet possibility rather than a looming event. Boltzmann brains represent a strange theoretical possibility, fully formed conscious structures arising briefly from random quantum fluctuations in an otherwise empty universe. Named for the physicist whose work on entropy inspired the idea, these fleeting minds would form by chance rather than by biology. They would appear, perceive nothing for an instant, and dissolve again. Whether such events could ever truly occur remains deeply uncertain. The concept exists mostly as a thought experiment testing what infinite time and empty space might allow. Named after the mathematician Henri Poincaré, a recurrence theorem suggests that any bounded system will eventually return to a state very close to where it began. Applied loosely to the cosmos, this raises the odd possibility that the universe's arrangement of particles could someday repeat itself. The time scales involved dwarf anything humans can meaningfully picture. Whether the idea even applies to an ever-expanding universe remains debated among physicists. Still, the theorem lends a strange, cyclical shading to the far future. Given a span of time longer than numbers can meaningfully describe, quantum fluctuations might, in theory, recreate our entire universe purely by chance. The mathematics behind such an event technically allows for it, however astronomically improbable. It would require every particle to align precisely as it once did, through nothing but random chance. No evidence suggests this has ever happened, or ever will. The idea remains a curiosity at the edge of physics rather than a prediction. Cosmic microwave background will stretch so far that its wavelength grows longer than any instrument could ever hope to measure. This faint afterglow of the early universe, already ancient, will keep redshifting as space continues expanding around it. Eventually, its energy will fall below any meaningful threshold of detection. What was once the clearest evidence of the universe's birth will simply fade past the reach of observation. Its story will continue, even if no one remains able to read it. Any civilization surviving far enough into the future would look upward and find no stars at all. Cosmic expansion would have carried every galaxy beyond the reach of light, leaving only an unbroken black sky. No familiar constellations, no distant glimmers, nothing to mark direction or time. Such observers would inherit a universe that looks, from the outside, almost featureless. And yet within that darkness, the same physical laws that shaped our own sky would still quietly hold. Let the mind settle like a single candle flame, lowering into its own pool of wax. The light growing smaller, but never anxious about growing smaller. There is no need to hold the flame steady. It simply rests, unhurried, until only warmth remains where the light once stood. Let your breathing take that same shape tonight, small and steady, needing nothing else from you. Physicists, studying the deep structure of space-time, wonder whether it could eventually settle into a state of total stillness, every ripple and fluctuation smoothed away. In such a state, the fabric of existence would hold no motion left to measure. No waves would pass through it, no vibration would remain. It would simply be unchanging for as long as anything could be said to exist at all. As the universe keeps expanding, it will stretch the wavelength of every remaining photon toward nothing, draining each particle of light of its last measurable energy. Radiation born in violent, brilliant moments will end up so stretched that it carries almost no signal at all. What once crossed galaxies as brightness will fade into an imperceptible hum, present everywhere, detectable nowhere. Whatever information survives from the universe's long history will eventually spread so thin across the growing cosmos that no instrument, real or imagined, could reconstruct it. Every event, every pattern, every trace of what once happened becomes diluted past recognition. The record technically remains scattered infinitesimally across space, but in any meaningful sense it can no longer be read. Across the whole of space, temperatures will drift down toward absolute zero, the coldest state physics allows. No pocket of warmth will remain to interrupt the descent. Even the last embers of stellar remnants will have surrendered their heat to the surrounding dark. The universe will settle into a uniform, motionless chill, colder than any night sky we have ever known. Every chemical reaction, every nuclear process that once powered stars and shaped planets will have permanently stopped. No fusion will light a core. No bond will form or break. The elaborate chemistry that built rocks, oceans, and living things will belong entirely to the past, a brief and remarkable interval in an otherwise motionless cosmos. In this far future state, the line separating empty space from matter grows almost impossible to draw. Particles become so sparse and so evenly spread that a given region of space and a given region of near vacuum look essentially identical. What we once called emptiness and what we once called substance begin to mean the same. Thin, uniform, nothing much of anything. The last organized structures, whatever faint architecture still lingers, will dissolve into a smooth and featureless quantum vacuum. No clusters, no filaments, no shapes worth naming will remain. Only the underlying field itself persists, humming at its lowest possible energy, undisturbed by anything resembling form. Certain theoretical models suggest that this seemingly final vacuum might not be the true end. A random quantum fluctuation, however improbable, could tip a small region into a fresh burst of inflation, inflating outward into an entirely new universe. If such a thing happened, it would carry no memory of what came before, beginning again from conditions unimaginably different. Eternal inflation, an idea explored across theoretical cosmology, proposes that our universe might be just one bubble among an unimaginable number of others, each one its own separate expanding pocket of space-time. These bubbles would never touch, never share light or history, forever isolated from one another. If true, our entire vast universe would be only one small chapter within something far larger and far stranger than we can picture. Loop quantum gravity, a framework explored across theoretical physics, predicts that spacetime itself may dissolve into countless discrete units at the smallest imaginable scale. Rather than a smooth, continuous fabric, space might resemble something closer to fine grains, each too small to ever measure directly. If true, even emptiness would have a hidden texture. The idea remains unproven, but it reshapes how physicists imagine the deepest layer beneath everything. Let your jaw loosen now, just a little more than before. Let the muscles around your eyes forget their shape, heavy lids resting without effort. Behind your closed eyes there is only a low, easy darkness, soft and undemanding. Nothing there asks to be looked at. Your face, so often holding small tensions all day, can finally set them down, smoothing into stillness like water losing its ripples. Beyond the farthest edge of what light will ever let us see, the multiverse hypothesis suggests other universes may already exist. They would lie beyond our cosmic horizon, forever unreachable, their light never destined to arrive here. Whether such universes are real or only a mathematical possibility, no observation has yet confirmed. Still, the notion widens the mind gently, hinting that our vast universe might be only one among an unknown many. A number of theoretical models suggest that time itself could restart under an entirely new set of physical constants. Gravity, light speed, even the strength of atomic forces might reset to different values in some future or parallel state. Such an event would erase every trace of the universe we know. It remains speculative, resting on mathematics rather than evidence, yet it offers a strange comfort. Endings need not be final in the way they seem. The far future universe will remain dark, cold, and profoundly still for the rest of eternity. No new stars will ignite. No warmth will gather anywhere within its endless volume. Whatever structures once shone across billions of years will have long since faded into an even, featureless dark. This state, once reached, has no reason within physics to ever change again. Dark energy's true long-term behavior remains one of cosmology's biggest open questions. It pushes galaxies apart at an accelerating rate, yet no one fully understands what it is or whether its strength stays fixed. Some equations treat it as a constant, others allow it to shift across cosmic time. Until better measurements arrive, its ultimate role in the universe's ending stays genuinely unresolved. The rate of cosmic expansion could still shift if dark energy's underlying nature changes over time. A slight strengthening might tear space apart faster than expected. A slight weakening might slow the drift of galaxies, or even someday reverse it. Current data cannot yet rule either possibility out. The universe's final shape may depend on a property still hidden from every telescope. A recurring idea in theoretical cosmology holds that the universe could cycle through repeated expansions and contractions. Each cycle would end in a collapse, only to rebound into another beginning, again and again, across unimaginable stretches of time. Such cyclic models remain unproven, resting more on elegant mathematics than confirmed observation. Still, they offer a picture of endings that quietly become beginnings. The eight-pyrotic model proposes that colliding brains, vast hidden membranes existing in extra dimensions, could trigger an entirely new cosmic cycle. In this picture, our Big Bang was not a beginning from nothing, but the echo of two such brains meeting. Afterward, they might separate, drift, and collide again far in the future. The idea remains highly speculative, built from string theory's more exotic corners. The conformal cyclic cosmology model proposes that each cosmic era rescales smoothly into the next, without any sharp division between an ending and a beginning. As one universe stretches into its coldest, most diluted state, its structure might mathematically resemble the hot, dense conditions of a fresh Big Bang. Under this rescaling, an ending and a beginning could, in a sense, become the same moment. Black hole evaporation, according to one speculative proposal, could seed the conditions for a fresh Big Bang. As a black hole radiates away its final mass, the immense energy released could curve spacetime into a new expanding bubble. This idea borrows from theories treating each black hole's interior as the seed of another universe. No observation confirms it, and the mathematics remains far from settled. That would make each black hole's ending a distant beginning. Theoretical physics keeps exploring modified gravity models that could replace dark energy explanations entirely. Instead of an unseen substance filling space, these theories adjust gravity's own equations across the largest cosmic scales. If correct, the universe's acceleration would arise from geometry rather than a hidden ingredient. The debate remains unresolved, testable only through future precision measurements of galaxy motion. Either explanation, if confirmed, would rewrite a central chapter of cosmology. Breathing slows on its own now, unhurried, each cycle a little longer than the last. The exhale especially can stretch out, releasing more than just air as it leaves the body. With every breath out, shoulders settle a fraction deeper into the mattress. There is only this rhythm now, rise and fall, carrying you further from the day. Let each next breath arrive whenever it wants, drifting you deeper with every slow cycle. Gravitational wave observatories being planned for the coming decades could someday detect delicate echoes of the universe's earliest moments. Ripples from the Big Bang itself, stretched and softened by billions of years of expansion, could still be moving through space today. Current instruments cannot yet reach the needed sensitivity. Future detectors, built with steadier mirrors and longer arms, could finally catch that primordial hum. It would be a message from the very first fraction of a second. Cosmologists continue debating whether entropy will keep rising indefinitely, never truly reaching a fixed maximum. In many models, disorder increases without bound as complex structures dissolve into pure heat. Others argue entropy must plateau once every possible configuration becomes common. The mathematics of a universe expanding forever remains genuinely open. Either way, the arrow of time seems to point only outward, away from order. Quantum states available to the universe's remaining particles multiply into numbers almost impossible to write down. Even a single decaying particle can occupy an enormous range of possible configurations. Across the whole of a nearly empty universe, that range grows beyond ordinary comprehension. Physicists describe it using exponents stacked upon exponents. It is a strange kind of richness, hidden within a cosmos that looks, from a distance, almost featureless. A fully evaporated black hole leaves behind only a last, dim burst of thermal radiation. In its final moments, the shrinking hole grows hotter and brighter, releasing energy in a rapid outward flash. That flash carries away whatever mass remained, spreading it thin across space. Afterward, no trace marks the spot but ordinary vacuum. It is a quiet finale to what was once among the densest objects in existence. Hawking radiation causes black holes to shrink at an accelerating pace as their mass drops. Smaller black holes are hotter, radiating energy more intensely than large ones. As mass decreases, temperature climbs, and evaporation quickens further still. This runaway process means the final stage of a black hole's life unfolds far faster than its beginning. The last sliver of mass disappears in what looks, on a cosmic timescale, like an instant. Charged black holes may evaporate a touch faster than neutral ones carrying the same mass. Their electric field adds another channel through which energy can escape into surrounding space. The difference is subtle, rarely significant, across a black hole's long life. Near the very end, though, small effects like this can shift the timing of its final flash. Physics keeps track of even these delicate asymmetries. After the last black hole vanishes, gravity's dominant role across the largest scales of the universe will end. For billions of years, gravity gathered matter into stars, galaxies, and dense collapsed remnants. Once those remnants are gone, only a thin, dispersed field of particles and radiation will remain. Gravity will still act, technically, between every remaining particle. But its grand architectural work, building structure from raw matter, will be finished. Photons will become the most common form of energy, remaining in the far future universe. Long after stars and black holes fade, light itself will still be traveling, stretched and thin, through the emptiness. These particles carry no mass, so they can outlast almost everything built from matter. Trillions of them will drift, unblocked, across distances too vast to measure. In the end, light may be the universe's most enduring resident. Electrons and positrons may become the last stable particles roaming the cosmos. Long after protons and neutrons have broken down, these lighter particles could persist, drifting through the emptied universe. Occasionally, an electron and a positron will meet, annihilating into a soft burst of light. Such meetings will grow rarer as distances between particles stretch ever wider. Eventually, only scattered survivors will remain, spread across unimaginable stretches of space. Dark matter particles, if they exist, may also eventually decay into radiation. Physics does not yet know what dark matter truly is, so its ultimate fate stays uncertain. Certain theoretical models suggest it could break down over spans of time far longer than the universe's current age. If true, even the invisible scaffolding that shaped galaxies would dissolve into light. The unseen framework of the cosmos may not be permanent after all. Feel the weight of your body now, settling into the mattress beneath you. Let your feet grow heavy first, then your calves, your knees, sinking a little deeper with every breath you take. That heaviness spreads upward through your hips, your back, your shoulders, releasing whatever the day was holding. Your arms rest, loose and full, at your sides. Even your head grows heavy against the pillow, still, unmoving, held. The concept of an observable universe becomes meaningless once expansion outpaces the speed of light. Regions once visible will slip beyond any possible signal, no matter how long one waited. Light from those places will never arrive here, and light from here will never reach them. The boundary that once defined what could be seen will simply stop applying. Distance itself will win the race against light. Space itself will keep stretching, without pause, if dark energy remains as steady as it appears today. Galaxies already rushing apart will recede faster still, their light stretching redder with each passing age. There will be no final edge, no wall where the stretching stops. It simply continues, indefinitely, carrying everything further from everything else. Distance becomes the universe's most permanent feature. The acceleration of cosmic expansion may continue increasing, without any theoretical ceiling holding it back. Current measurements show galaxies pulling apart faster now than they did billions of years ago. If that trend continues unchecked, the pace of separation could keep climbing forever. Physics has no known law demanding a limit to this growth. The universe's outward push may simply keep gathering strength. Certain models predict that accelerating expansion could eventually rip apart atoms themselves. If dark energy's strength keeps rising, the stretching of space could overpower even the forces binding particles together. First galaxies would separate, then stars, then planets, and finally the atoms making up all matter. It is a distant and uncertain possibility, resting on assumptions about dark energy's future behavior. Still, the mathematics allows for such an ending. Planets, stars, and even subatomic particles would be torn apart in sequence under a Big Rip scenario. Galaxies would separate first, drifting beyond each other's reach. Then solar systems would unravel, planets flung from their stars. Stars themselves would come apart, followed at last by the atoms holding all matter together. Each stage would arrive faster than the one before it. Every gravitationally bound structure could eventually be pulled apart under a Big Rip. Galaxy clusters, individual galaxies, solar systems, even moons, orbiting their planets, none would remain intact. The very forces holding matter together would lose their grip against the growing stretch of space. What once felt permanent, gravity's quiet architecture, would come undone entirely. Only scattered fragments would drift where structures once stood. A Big Rip would bring the universe to its end within a finite, calculable stretch of future time. Unlike the long fade of other endings, this one carries an actual clock. If dark energy's strength keeps climbing without limit, physicists could someday plot the very date when galaxies, stars, and atoms come apart together, every structure would reach its unraveling on the same countdown. It remains one of the few cosmic finals with a true finish line. If dark energy remains stable, the universe likely drifts toward an eternal heat death instead. There would be no finish line here, no final hour marked on any clock. Galaxies would simply fade, stars would dim one by one, and the fabric of space would keep loosening its hold across unending time. Current measurements suggest dark energy's density is holding steady, favoring this slower, unhurried outcome over any sudden ending. Heat death predicts a universe of uniform temperature, with no usable energy left anywhere. Every pocket of heat, every gradient that once powered motion and light, would even itself out completely. Picture a still lake with no current, no ripple, no difference between one drop and the next. Once everything reaches the same faint warmth, nothing remains to flow from one place to another. After heat death, no further work or change could occur anywhere in the cosmos. Without temperature differences, nothing pushes and nothing pulls. Chemistry falls silent. Light stops mattering. Motion loses any consequence it once had. The universe would simply exist, unmoving in any meaningful sense, forever balanced at the same faint hum of leftover energy, with nowhere left for anything to happen. Somewhere far off, a low hum rises and fades, the way a house settles once the lights go out. It comes and goes without asking anything of you. Let it be the last sound you notice tonight. Your breath can follow its rhythm, rising softly, falling away, needing no effort at all. The room holds you exactly as you are, and that hum keeps arriving, keeps receding, asking nothing in return. Cosmology now leans toward heat death as the statistically most likely ending, weighed against every other possibility. Among all the futures the equations allow, this quiet fading appears the most probable path, given what current measurements of dark energy suggest. It is not a certainty, only the outcome the numbers favor most, resting gently atop everything cosmologists have measured about the universe's expansion so far. Nearly 13.8 billion years ago, everything now unfolding began in a single moment. From that first instant came galaxies, stars, oceans, and every thought ever carried inside a mind. Whatever ending the universe eventually reaches, it started here, in one point of impossible density and light. The vast stretch between that beginning and any far future ending is the whole of everything that has ever happened. Just as the universe began in change, its farthest future promises only lasting stillness. Between those 2 points lies everything you have heard tonight and everything you are. You have rested inside a story, stretching from one blazing moment to an ending beyond counting. And for now, none of it asks anything of you. Let your body sink into the dark, unhurried, and held. Good night.